Hi, this is Mrs. Kidman, and in this video, we're going to be discussing how we can solve exponential equations. So before we do that, let's take a second to review a couple of properties of logarithms that we've learned before. So we know that the log of any base evaluated at 1 is going to be 0. And the reason why we know that is, remember, logs and exponentials are inverses, so we can rewrite them as one another. And in this case, that means the base raised to 0 is going to be 1. Well, that's true. Any number raised to the power of 0 is 1. Because really what a logarithm is saying is, how many times do I have to divide a number by something else until it gets to 1? Well, in this case, how many times do I need to divide the number 1 or by b? Well, none, because it's already at 1. The other one that we've talked about before is the fact that regardless of the base, if we evaluate it at the base, then it's going to equal 1. And the reason why is any number to the power of 1 is itself. Now, here is another property that we have not yet discussed, but is super crucial when it comes to properties of logarithms. Now, this is where that situation of inverses comes into play with an exponential versus the logarithm. Because they're inverses of one another, that means they cancel each other out. Therefore, if I have a log base b of b to the power of y, this thing equals y. The reason why is because if I do b to the power of y, well, that's going to be equal to b to the power of y, right? So we can rewrite it by taking our base to our solution and raise that to our exponent. So as we're using this and solving exponentials, really what we're going to be doing is we're going to be using this property over and over again, because what we're going to have is two different things with various bases, or base being equivalent to a constant. And we're going to use this idea of a logarithm to get rid of our base, so we're just left with our exponents. So let's take a look at a couple of examples here. So in this first one, we want to solve the exponential of this equation. Now, when it comes to solving exponentials, the very first thing you want to do is get the exponential alone. And so what that means when we talk about getting it alone, what I want to do is I want to make sure that there is nothing being added or subtracted to it. So no add or subtracts. And we also want to make sure there's no numbers being multiplied or divided. And we're going to do it in this order that we talked about it here. So first we want to get rid of our add or subtracts. Then we want to get rid of our multiply divide. The only time when that is not going to be the order is when we have a multiplier divide that applies to the whole thing. So if it's like 3 times something, and we'll see an example of that later. So first we want to get our exponential alone. So we're going to do that here. Plus 4, 10, x plus 7 equals 14. Okay, you can see how we got that exponential all by itself there. It's just 10 to the power. There's nothing multiplied or added to it. So we got that alone. Our second step is we are going to do what we call log it, is kind of how I want to describe it. Now, that's not the official term, but what we're going to do is we are actually going to apply a logarithm of the same base that our exponential is to both sides. And the reason why we can do that is, remember, this property here that we talked about says that the log of any base times the base to that power, well, that's going to get rid of both of those and equal just what our power is. And so what that'll do here in our example is it will get rid of this 10 and give us just our x plus 7 equals whatever that other side is. So it gets rid of making it a power and turns it just into something we can solve using our basic algebra techniques. So looking at this one here, what I'm going to do is I'm going to do the log of base 10. You can write the 10 or not. Remember, we typically don't when it's base 10. The log of 10 to the x plus 7 equals the log of 14. Now notice a log is a function, just like squaring or square rooting. So as that operation of doing it, we need to do it on both sides of our expression here. So we are going to apply that log base 10 to both sides. So now we have a log base 10 of x to plus 7 and log of 14. Now using this property here, we know that because it's a base 10 and we have a 10 here, that this is just going to equal our exponent. So here on our left-hand side, we just have x plus 7 is equal to the log of 14. Now we can use a calculator to evaluate that as we would like, or we cannot. And ultimately our goal when it comes to solving is we're trying to get this x by itself. That's what we're doing here. So I'm going to subtract 7 from both sides, and I end up getting that x is equal to the log of 14 minus 7. So what does this mean? Well, if we really wanted to figure out what x is equal to, we can actually type that straight into our calculator. So the log of 14 minus 7, and that is going to give us, I'm going to round here to 4 decimal places, negative 5.8539. Okay, so this is going to be what that ends up equaling. So if I put in x equals negative 0.8539 into this expression here, it'll equal 10. And we can check that if we would like. So 10 to the power of negative 5.8539 plus 7 minus 4, that should equal 10. So we want to know, does that equal 10? Well, let's go ahead and take a look at what happens when we do that in our calculator. So 10 to the power of negative 5.838539, oof, plus 7 minus 4. Okay, so I got 9.999. Now, it wasn't perfect, but that rounds up to 10, right? So we can see what we're doing here. We're trying to solve for that. So let's take a look at 2 more examples in which we are solving these exponentials, following through these same steps. So again, we're going to get our exponential alone. We are going to, quote unquote, log it. And then the last thing we're going to do is solve for x. Okay, so those are our 3 steps here. Let's take a look at this example here. This one, this is a great one. So this one is very similar. Now in this case, we have an e. Now remember, when we log something with base e, the log of base e is often referred to as the natural log, or sometimes written as ln. So when we go to do that log it, quote unquote log it step, what we're gonna do is we want to use the natural log in this case instead of the regular one. But before we get there, our very first thing we need to do is get our exponential alone. So I wanna check, do I have any add or subtracts here? And I want to get rid of them. And in this case, I do. I have a plus 5. So I'm going to get rid of that plus 5 from either side. And we end up getting e to the x minus 1 is equal to 10. Then I want to check, do I have any multiplier divides? In this case, I do not, so we don't have to worry about it. But typically, that's the other thing we need to do before we get a loan. Then our second step is to log it, meaning we're going to apply the function of a logarithm to either side so we can get rid of that exponential. So in this case, we're going to have the natural log of e to the x minus 1 is equal to the natural log of 10. Now the natural log of e to the x minus 1, based on this property here, is just going to be x minus 1. Then on this side, we have the natural log of 10, which is just a number. And our third step is going to be to solve for x. So we're going to go ahead and do that here. We can add 1 to both sides, and we get that x is equal to the natural log of 10 plus 1, which might mean something to some people. But for us common folk that don't know exactly what the natural log of 10 is, especially the natural log of 10 plus 1, well, what that turns out to be is we end up getting a fantastic 3.3026 when rounded to 4 decimal places. So that's how we can evaluate that one, just like before. Now, there are lots of different ways that we can look at it. We have something like this, where in this case, we don't have an add or subtract, but we have a multiplier divide. Here is another case in which we have a multiplier divide. And this last one here, we've got 2 different powers. So we're going to look at 2 more examples here. We're going to take a look at this one with our e. And we're also going to take a look at this one where they have the same power. So again, we're going to follow through our same steps. We want to get our exponential alone. So in this case where we're trying to get it alone, we need to get rid of that 7. So I'm going to divide by 7 on both sides. And that ends up leaving me with an e to the power of 3x is equal to 2/7. Now 2/7 does not divide into something pretty other than being 2/7. And that's totally fine. Notice how in this case we did not have any add or subtract that we had to get rid of. But we did have a multiply and divide that we needed to get rid of. And so we always want to make sure that we are getting rid of both of those things before we move on to step 2. Now in step 2, that's when we are going to do our log it, where we apply that log function. In this case where our base is e, we want to apply the natural log. Every other time we will apply a log of the base of whatever our base is here. And you'll see that in the next example. So our natural log of e to the 3x is equal to the natural log of 2/7. And then we end up getting 3x is equal to the natural log of 2/7 after we simplify that natural log, that logging option here, because we know that these cancel just to our 3x. And our third step is to solve for x all over again. So here we go. To get x by itself, we're going to divide both sides by 3. So we know that x is equal to the natural log of 2/7 divided by 3. Now again, that means something to some people, but for those of us who are not quite sure what the natural log of 2/7 divided by 3 is, we can type that right into our calculator and we can end up getting -0. Let me put that negative in over here. -0.41 0.76 when we round to 4 decimal places. Now you'll notice that I'll typically round to 4 decimal places, but you can choose how many you round to. Now we're going to take a look at one last example here. In this case, we want to solve this exponential. Now there are lots of ways that we can solve exponentials. If they have the same base, what we can do is we can actually just set their powers equal to each other. And the reason why here is, remember, step one is we want to get our exponentials alone. Now in this case, we have exponentials on both sides. Therefore, they're both alone because there's no add or subtract that we're dealing with, and there's no multiply or divide. So we are totally fine. None of that exists. So we are good. Now our second step is to do our log it step. Now when they have the same base like this, we can actually log both sides. And that's why their exponents are the same, because if I do log of base 5 of 5 to the power of x is equal to the log of base 5 of 5 to the power of 2x minus 6, something like this, our log, base 5 and 5, they are inverses, so they cancel each other out, and all we're left with is that exponent. So that point in our lives when somebody told us the exponents are equivalent if the base is the same, the reason why is because if we apply a logarithmic function to it, those will simplify down. So x is equal to 2x minus 6, meaning we can then solve for x. In our third step, solve for x, we can subtract 2x from both sides. We end up with a negative x equals negative 6, which when we divide both sides by -1, we get x is equal to 6. Okay, so that is how we can do that. Now, when it comes to solving exponentials, a couple of quick reminders that might be helpful when it comes to exponents. If we see a rational problem, so a 1 over 36, we can rewrite that as a 6 to the power of -2. Now, this is super crucial because in this last example here, when we have two sets of exponentials that are equal to each other, in order to log both sides, they have to have the same base for our exponential. We can't just log a base 4 on one side and a base 7 on the other, because those are not the same property, not the same function. Just like square rooting and cubed rooting are not the same thing, log of base 5 versus log of base 10 are not the same thing. So we have to be consistent on what we do on either side. So in order to solve them with exponentials on both sides like we have here, we need to make sure they have the same base. And so if we have a 6 to the x plus 2 is equal to 1 over 36, we want to rewrite it like this so that we have something with a 6 on both bases. Another thing is if we have two things with the same base being multiplied together, we can actually rewrite it with our exponents being added together. And that is going to be very helpful when it comes to any problems with multiple exponentials on the same side. As long as they have the same base, we can combine them together. And lastly, sometimes we have numbers like 27 that is not the simplest form. So when you have a number, make sure that you double check its base with what we're going with, because the number 27 to the power of 1 is a true thing, but 27 is also the same thing as 3 to the power of 3. And so we want to make sure that we are aware of what some of these numbers can be rewritten as in a different base, so that we can use that concept when it comes to solving these exponentials. So if you have any questions, feel free to reach out, but that is how you can solve exponential equations. Please check out the next video in which we go through how we can solve logarithmic equations using some similar properties.